Non-michaelis menton kinetics. Yes, not everything. In michaelis menton kinetics is more the exception rather than the rule. So the things that we're going to talk about, and there's a lot of things we could say that's non-michaelis menton, is sequential reactions. Obviously, we're talking about enzyme reactions here, and hopefully that was apparent to you. But the first thing that's going to happen is all substrates are going to bind to the enzyme. All substrates bind to the enzyme. That's the first thing that's going to happen. The second thing that's going to happen is that the products are going to be released. All right, so let's talk about the mechanism for sequential reactions. So there's two types of mechanisms that we have for sequential reactions. These are the ordered ones, where the entry and exiting of the binding order of the substrates is ordered, and then there's also ones where the binding of the substrates to the enzyme complex is random. All right. And in both of these, regardless of whether or not it's an ordered or random, the hallmark signature of a sequential reaction is this thing known as a ternary, like tertiary or 3, complex, which is made up of exactly what it would sound like. So let's say that we just draw ourselves a ternary complex. Note that means we're talking about the number 3 here. So there's the enzyme. Here's my enzyme. There's the active site. There's the rest of it. There's a site there and all that. That's my enzyme. Whoop-de-doo. There's going to be substrate A. So substrate 1 is going to bind to it. And substrate 2 is going to bind to it. I have 1, 2, 3 things there. That's the ternary complex. The other thing, though, that's non-michaelis menton kinetics would be double displacement reaction. Abbreviated as double Ds. Yes, how vulgar of me. Anyways, this is where greater than one product is going to be released before all the substrates bind to the enzyme. Locally, we refer to these as ping-pong reactions, and I'll explain why they're called that in a second here. This is where the reactants, or in this case the substrates, and then the products are literally bouncing on and off the enzyme. Now, not all reactants and not all substrates are going to do this, specific ones here. We also have to have something released in doing so, and then the order of double displacement reactions causes conformational changes which provide the appropriate conducive site for the binding of the next one. So there's no such thing as a random double displacement reaction. They're all very ordered. The signature sign of a double displacement reaction is a substituted enzyme intermediate. This is exactly what it sounds like. This is a temporarily modified enzyme that's partially substituted. It contains part of the substrates involved in it. My book gives some examples of what this is, but basically this is the in-between process of the bouncing on and off the ping-pong reactions. And then the last thing that I wanted to mention, I'll do it in white over here, is the actual activity. The activities of non-michaelis menton enzymes, at least the brief ones that we're going to talk about. So there's the kinetics, and then there's the regulation. In this context, we're really mostly talking about allosteric. I was going to say that these are the the other allosteric ones, which I'm assuming that you know what allosteric enzymes are. I'm not going to really talk about that too much. But for the kinetics of these, they tend to have a sigmoidal curve. And what that means is, whereas when we plotted our velocity versus our substrate concentration, well, with the michaelis menton ones, we had a hyperbolic growth. It literally looks like that, like a sigmoid. It's sigmoidal. It's almost like a letter S, and then it branches off here. Some things that we could say about this sigmoidal curve is that the Km, there's obviously if we look at the point here, okay, the point at which we have half Vmax, the Km value is going to be low, but it's also wider. It's not as steep of an incline as we saw with the other one. So if Km is wider and larger, what this means is we have more enhanced control. I mean by saying more control, I mean that this is more susceptible to changes in concentration of substrate. That's what I mean by saying that. Hopefully that kind of gives a point to this. So for regulation, there's allosteric regulation. You should probably know what that is. Positive feedback. Positive feedback loops in this, or in endocrinology, or in general biology, is where the end product increases its own production. Okay, then the other one would be negative feedback, which in general biology you learned about this. Negative feedback is where the end product of a reaction decreases its own production. And that's it for that.